All right, we're going to talk a little bit more about polynomials and their roots. So first off, I'm going to start with imaginary roots. Imaginary roots always come in pairs, at least if your quadratic has real number coefficients. Then there is no way for that quadratic to have one imaginary root. So imaginary roots can be represented by sort of a dip that doesn't touch the x-axis. That guarantees there are at least 2 imaginary roots there. Now, there may be 4, or there may be 6, or there may be 8 hidden in there. It's hard to tell. And sometimes imaginary roots don't have an obvious dip. But we could use our rational root theorem and our Descartes' rule of signs to figure out how many imaginary roots there are. And more than that, when imaginary roots come in pairs, they come in a specific type of pairs. If one of the imaginary roots is 6 plus 2i, then the other one would have to be 6 minus 2i. Do you remember why that has to happen? The only way to multiply 2 factors with imaginary roots and have all of the i's cancel is if those imaginary roots are complex conjugates. Right? Remember conjugates, x plus 3, x minus 3. If I multiply that together, I get negative 3x and plus 3x and minus 9, and those two middles cancel, and I'm left with x squared minus 9, which is called a difference of squares. A difference of squares is created when you multiply conjugates. Well, the same thing happens when you multiply complex conjugates. So if I had x minus 6 minus 2i, and I multiplied it by x minus 6 plus 2i, I'm going to get x squared minus 6x, and this is also minus 6x, and then that would be plus 36, and then this one is going to be minus 4i squared. But I squared is negative 1, so I change that to a plus 4. But I skipped some. I skipped this one and this one. But what do you notice about those two terms? Because of the conjugate rules, they're going to cancel and turn out to be 0. Likewise, I skipped this and that. And those are going to multiply and be opposites and cancel anyway. So if your imaginary roots are conjugates, when you multiply the factors together, all of the i's go away, including the I squared. And so you end up with x squared minus 12x plus 40. And this is a quadratic equation that has 2 imaginary roots. So if you have if you know one imaginary root, it's really easy to find the other one. Okay? The other thing you need to remember is how to factor difference of squares and sum of squares. So if I add x squared minus 100, how does that factor? X plus 10 and x minus 10, and does it want you to find the roots? Okay, so it's going to want you to factor it and find the roots. X equals plus or minus 10. What if I had x squared plus 64? Does that factor? Not into real number answers, but if I did x plus 8i and x minus 8i, when I multiply that, I get x squared, and that's going to give me negative 64i squared, which turns into plus 64, and by the rule of conjugates, the other two terms are going to cancel. This and that cancel. So a difference of squares factors into real number conjugates. A sum of squares factors into imaginary number conjugates. So this would be x equals plus or minus 8i. All right? What if I had x squared, nope, that's not x to the 4th, thank you. X to the 4th minus 81. Is that a difference of squares? it could be written as a difference of squares. Is x to the fourth a perfect square? X squared and x squared. Is 81 a perfect square? Yes. So it's actually x squared minus 9 and x squared plus 9. Right, so this, breathe, breathe. So this one actually has a difference of squares and a sum of squares hidden in there. So x plus 3, x minus 3, x plus 3i, x minus 3i. So the roots are plus or minus 3 and plus or minus 3i. Now, the graph of this is a little bit deceptive. It's going to look like this. So that would be negative 3, and this would be 3, and that's going to be negative 81. And you can't tell that there are imaginary roots. There are none of those little whoop-de-doos above the x-axis. So sometimes imaginary roots are hidden and you can't actually see them. Okay? So if you look at your assignment, four, you're just going to factor it. Oh, it doesn't work. So for number 4, we can't factor it. There are no factors of positive 5 that add to be 4, so we need to use a quadratic formula. So it'd be negative b, which is 4. Well, let me write it out. Negative b plus or minus the square root of b squared minus 4ac over 2a. And it is up on the wall. It's kind of small on the bottom left corner of that equations paper. So 4 plus or minus the square root of 4 squared would be 16. Minus 4 times 5 times 1 is negative 20 over 2a. So 4 plus or minus the square root of negative 4 over 2, which is 4 plus or minus 2i over 2, which is 2 plus or minus I. Now, it says not only do you need to find the roots, but you need to write out the polynomial as a product of linear factors. So if those are the roots, what are the two factors? X minus 2 minus I and x minus 2 plus I. Those are the linear factors. Okay. So if you look down at number 9, a polynomial function is described. Find all remaining zeros. So number 9 says degree 3, which means what? There are 3 roots. One of them is negative 1, and one of them is I. What is the other one? Would be negative I, because that is the complex conjugate to positive I. All right, number 11 has 4 roots. 2 of them are given. What are the other 2? 3 plus I is the complex conjugate for that one. And negative 2i is the complex conjugate for this one. Okay? Somebody look up the answer. Somebody flip to the answer sheet. I never know what they're going to do in this book, and I didn't look it up. On number 17, do they write out the factors, or do they actually write the polynomial? Okay, that's what I thought they wanted. So if you look at 17, 17 is going to be x times x minus 1 minus 2i and x minus 1 plus 2i. Does everybody understand that? Now, when you multiply complex conjugates, skip all of the i's except for there's one I multiplication you actually need to do. When you multiply the I times the I, the last one. And I'm going to wait to bring in this x until the end. So I'm gonna do the complex conjugates first, and then I'll bring in the x. So do I need that? Yes, x squared. Do I need that? Minus x. Do I need this? No. It's going to cancel, so I skip it. Do I need that? Minus x. Do I need that? Plus 1. Do I need that? No. Do I need this one? Nope. Nope. And that's going to be minus 4i squared, which turns into plus 4. So x squared minus 2x plus 5. And then I'm going to bring this x in. So x to the third minus 2x squared plus 5x. So essentially, and I mean, you could do this in your head if you think a little bit about it. What we really did was x minus 1 times x minus 1, which you guys can do in your head, right? X squared minus 2x plus 1. And we also have to bring in that term. That's essentially all you need to do for complex conjugates, is do the square of the original binomial and then bring in the I squared term. So if you look at number 19, we're going to have x minus 1 times x minus 1, oops, minus 5i, or plus 5i, and x minus 1 minus 5i. So I would do these first. That way you can skip all the i's but the last one, and then bring that x minus 1 in. Okay, and then 21. How would you compute 21? What's the easiest way to multiply 4 of these together? Do these two together and those two together. Do you know what the last two are going to be without doing any multiplication? It's going to be x squared plus 9, because it's a sum of perfect squares. So x squared plus 9, and then do those two, and you'll get some other quadratic, and then you'll multiply those together. Okay? You could make these really, really hard. If you did them in the wrong order, you're going to end up with I values that are really long. And in the end, all of the i's are going to cancel. So when you multiply them together, just do it in a smart way to save yourself a lot of work. Uh-oh, Braden's twirling his glasses. Bad sign. All right, get to work.